sphere. So this is really a Planck sphere. And that's where the qubits live, in a Planck sphere. And there are like really cool simulations that you can look at them. Okay, so I have these qubits. They have a lot of information kind of encoded into them. I didn't do anything yet, right? When you perform a computation, you have your bit strings of information, but you need to pass through logic gates, correct? That's how you achieve, that's how you do a computation. You gotta pass through logic gates. Well, how do I do that here? If I have this kind of non-traditional bit of information, well, what do the logic gates look like? Well, the logic gates are just what are called unitary operators. They have to respect the rules of quantum mechanics. Let me see if I want to go back to my slides.
So do the logic gates use the algorithms that you're talking about?
You choose your logic gates based on what you want to accomplish. Yeah, and I'll show you some. I'm going to show you a bunch of logic gates. But I did want to write down just another example of 2 qubits, what the vectors look like. So for 2 qubits. Just so if you read some of this stuff, you know what the language is. So you can kind of interpret the language. So 2 qubits live in 2 squared 4-dimensional space. And so for the Dirac notation, and then we would have 0, 1. And let me just make sure I have it going the right way. Yep. And then we would have, let's say, 1, 0. And then we would have 1, 1. Okay. What I'm doing is I'm writing shorthand. This is what, remember, we call Dirac notation. It's a ket. It's an element which lives in a 4-dimensional space, but the 4-dimensional space is actually, it's what's happening behind the scenes, which I'm not writing down, is that we have a tensor product here. Okay? Don't worry about it if you haven't learned about it. This is just so that you can untangle what the notation means. Another way you might see it written in a paper or in a book is you may see this written in terms of Arabic numbers. I've even seen this in my book that I love to read. This one, they write a lot of things down for the shorthand in the Arabic numbers without having the bit string. So they would write this like this, 0, 1, 2, 3, and it's understood what it means, that the binary equivalent, right? It's just a shorthand. So I just want you to see so you can untangle mathematically what is it, what am I even reading, what am I looking at. So if we're going to operate on these qubits, then we need unitary operators, which are matrices, right? Which we multiply in front, and it transforms this to another column vector. It goes somewhere, but we've got to be clever about how we set it up. Okay. Okay. Let's keep going. Marianna.
So maybe you mentioned this already. So can you tell us what these mathematical objects are representing physically? Like, what is a qubit physically? What is making a qubit? Maybe you can just
right here. Let's turn this back on.
So it's the
I got it. Thank you.
So you said Google has 53?
Yep.
2 to the 53? It's 2 to the 53?
53 qubits, so it's 2 to the 53 space. So here, so this is what a qubit physically is. So we said that it can be an ion, right? It could be a spin 1/2 particle, or it could be a photon, physically realized.
So did you guys talk about spin in your class with Professor Berman?
where, I don't know if that's had anything to do with this, but they talked about like spin. And, yeah, and like photons, because it's polarized. We did that in class.
Polarize light, yeah. So there are different ways of realizing it. So I think that, you know, it's, and we can talk about this more later, but it's a big, huge engineering challenge to create a machine that's stable at room temperature. Because what happens is we have what's called decoherence. So you start running your computation and noise from the outside world comes in and just makes a disaster and like crashes your computer. So like how do we have it so that it's stable and it's not at like 3 degrees Kelvin, like, because that's like what they have. So it depends on like the physical realization. I remember back when I was in college or when I was in grad school, like the talk was that they would have these ion traps and try to get, you know, a string of ions linearly aligned. Because with a Paul trap, I know you can trap them in kind of like in space, but to have them linearly aligned is maybe a different kind of challenge. So there are all these challenges of like, how do we actually build this thing? So it looks like they're making a huge headway, you know, as we go. And then, again, we can talk about this more later, but, you know, a lot of the initial quantum computers were very task-specific. So they were able to factor 15, I think it was in 2001, I was a grad student, I was really excited about this. We were all like in the hallway, did you hear they factored 15? Super excited. But it was programmed just to factor 15. It wasn't like you can run matrix multiplication on that computer. You couldn't do anything but factor 15. Now, the computer that Google created, that 53-qubit computer, it's programmable. So you can run whatever algorithm on it, which is kind of, to me, that was groundbreaking when I heard that that was programmable, because until now they haven't been. They've been very specific.
How big is that computer?
I don't know physically what it looks like. I have the article if you want to look at it, but physically, I don't know. Okay, so we talked about this. So for those mathematically inclined among us, here's the Dirac notation with the cats. This is called the dual space. There were all the maps, and those are the bras. And so it took me a couple years to finally realize physicists are kind of tongue-in-cheek in this way. No, I don't mean to insult you in any way. When you put it together, it's a bra. I was like, do they mean bracket? Bra and cat? I was like, oh. I was like, they just mean bracket. So I thought that was really hilarious. I was like, all right. So the bra-cat notation. Okay, so like we said, how are they different? They exist in a continuum of states between 0 and 1. It's neither 0 nor 1. It's kind of everything all together at once. And we can easily write down a linear combination, and we have probabilities that when you measure it with through the lens of the computational basis, it's going to collapse and either be 0 or be 1. And so using sigma notation, here we have it, and we've got to make sure that all of these probabilities, that they're normalized, meaning they sum to 1. Okay, so this relates. How is this relating to quantum mechanics? Well, we talk about how could it be 0 and 1 at the same time. So I'm sure many of you are familiar with this whole idea of Schrodinger's cat. You guys are familiar with it? Some of you not familiar with the kind of thought experiment here. So the thought experiment goes like this, that we have a cat, we have the cat in a sealed box, and we have some poison in a vial, and then we have a Geiger counter next to it. So we have a little amount of radioactive material, and if this radioactive material decays and emits a particle, the Geiger counter will register that and crack the vial of poison, kill the cat. This is all happening behind closed doors. So we have an observer outside, we have the cat in the box. So according to the observer on the outside, the cat exists in this weird state that's neither dead nor alive. We don't know. When we observe the cat, it's going to be either dead or alive. So the wave function of the cat collapses to be dead or alive. Kind of the same idea when we think about the qubit. When we perform a measurement, the qubit is either going to be in 0 state or 1 state. It's not going to be both. right? So this is the version of quantum mechanics that's observer dependent. This may or may not make sense to you. As you learn more, you can talk more about it. Right? Definitely talk more about this with your physics instructors. Okay, so what's the main advantage? So he found this quantum parallelism principle. So he's saying that what we can do with this is we can evaluate a function. We can do one function evaluation on many numbers simultaneously. You can't do that on a computer. You put an input, you get an output. You can't simultaneously do one function evaluation on many numbers simultaneously and get an output. It just doesn't work that way. And it exploits the superposition of states. Okay, so maybe let's look at this. Let me show you one example and then we'll go to this video. And this video very clearly kind of highlights how a classical computation unravels in a different way than a quantum computation. So let me show you kind of a walkthrough of one and then we'll go to the video. Walkthrough. So, as we mentioned, quantum gates move the vector, meaning the vector representing our qubit, right? Move this vector around in the sphere. Right? If it's higher than two-dimensional, it's a sphere, otherwise it's just a circle. Okay, so let's look at an example of a basic computation on two qubits. So here's an example of a basic computation on two qubits. Okay, so it looks like this. Let's start, for instance, 0, 0. We're going to apply a quantum gate. I'm not showing you the gate right now. We're going to apply a quantum gate. I'll show you some examples where I tell you what the gates are. And then we get here. Quantum gate, it's just a unitary operator. And I'll write it down if you want in terms of vectors instead of the Dirac notation is throwing them off. Okay, apply another quantum gate. Apply another. And suppose here we end up with this. 1 over. Okay, and now you observe. Here at this point, you observe. Now we're looking at the cat. Is it dead? Is it alive? What happened? And the wave function of the system collapses to a single state. Let's say in this case, which one? Let's do this one. Okay. So here's a very basic procedure. We start with our qubit. Actually, we have 2 qubits. So we start out where we're living in 4 dimensions, 2 square dimensions. We start with this. It's just a vector. We apply a matrix to it, that's a unitary operator, that's our quantum logic gate. We get here, midway. Now we'll apply another one. We get this. So remember I told you kind of how to interpret it. That these really give us a notion. They're related to probabilities. So when we perform a measurement, we have a 1/2 chance of finding the system in state 0 or 1. We have a 1/6 chance of finding the system in a state 1, 0, and a 1/3 chance of finding the system in the state 1, 1. So if I do this experiment, I run the experiment 100 times, 50 times, I'll get this as my answer to my computation, 0, 1. 1/6 of 100 times I'll get this, right? 33 times I'll get 1, 1. So this kind of gives you an idea. So here are the tricks that we can play. Because what comes out on the other end is really probability based, we can manipulate these so that the right answer, these are called amplitudes, right? I'm talking about them as probabilities, but they're not strictly probabilities. They can be negative. Probabilities are not allowed to be negative, right? They can be complex numbers. Probabilities are not allowed to be complex numbers. So I'm saying it kind of tongue-in-cheek in a sense. But really what happens is I can arrange it so that when I apply my quantum operators, the amplitudes of the right answers reinforce each other like a wave. And the amplitudes of the incorrect answers cancel each other out, kind of like the way waves work, right? The wave function. So that in the end, when I make my measurement, most likely I'm getting the right answer. So that's the clever way that you set up your algorithm to work in your favor. And it's not easy to come up with a truly distinct quantum algorithm. There are really only 2 truly distinct quantum algorithms. One is Shor's for the factoring, and one is Grover's for the searching. And every other quantum algorithm that's out there is some modification, basically, of those 2 core ones. So if you could find a new one, that would be kind of monumental. So now that I kind of walked you through one, and if you want later, I can even give this to you. Instead, if you don't like the Dirac notation, I can write out the vectors if you feel more comfortable with it. But let's look at how this quantum parallelism principle works. Oh, do we have volume? Maybe we can make the speaker a little louder?
Yeah.
Through here, it's not really.
Is it on?
Yeah.
There.
And, okay, let's see. Try. Okay, let's hear.
What's the value of all this content?
Can you guys hear? Or is it too low?
I think it's pretty good. I think it's on the plug and then. Oh, right. It's like a green one.
Okay, so then it's going to be really loud when we make this before we all go.
I remember you following this.
No.
But is this the right? We can try it. I guess it's only. Try it?
We good? Okay, let's try.
Why quantum computing is
Thank
so
you.
interesting. To answer that, let's look at the 6-qubit quantum computation. It's computing using a sphere in 64-dimensional complex space, because 2 to the 6 is 64, which sounds complicated. But here's the important part. It only took 4 steps to find this state. If we wanted to find the same state using a classical computer, it could take thousands of steps. Why? The classical computer can only be in one basic state at a time, so it has to follow one branch down the tree at a time. But the quantum quantum computer processes an entire level of the tree each step. So this computation only takes 4 steps. When a quantum computer is in a superposition, it's processing a bunch of classical states in parallel. But remember what we talked about earlier. The quantum computation will only return one state, which is determined probabilistically based on its final superposition. This means we may have to run the computation a few times to gain the information required, but it's still way less than trying to compute it classically. This small example doesn't really convey how big of a deal it is that quantum computers take exponentially less time than classical computers. Probably the most famous example of this is Shor's algorithm.
Okay, we'll talk about that shortly. Let's go back. Okay, so I didn't really tell you what the logic gates looked like, right? I just said apply a quantum logic gate, and we went from one step to the next. Let's talk a little bit more about these logic gates. They have to be what are called reversible. So if you study computer science, for instance, there's one popular gate you all learned, it's the AND gate, right? Where that's going to give you, if we have 2 inputs, they're both 1, what do you get as the output for an AND gate? 1. Every other circumstance, 0, 1, 1, 0, 0, 0, what's the output? 0. Okay. If I just look at the output of an AND gate, can I know definitively from where it came?
No.
If I give you output 0 and I say went through an AND gate, what was the input? I have 3 options, right? I can tell you what the 3 options might be. I don't know. That gate is not a reversible gate. So to have a quantum logic gate, it's got to be reversible. Why reversible? Because quantum mechanics in the Hamiltonian formulation describes only reversible processes. So I got to be able to go forward, but I also got to be able to go backwards. So we've got to cleverly design our logic gates so that, given the output, I can always recover the input. Now I can get really clever about it. I can say, I have a marker or a flag that's an extra bit that goes along for the ride, so that I know when that flag is set to 1, something happens. That goes along for the ride. On the other end, I can look at my output and I can look at the flag and I can say, oh, the flag was 1. I know where it came from. So you get smart about making these gates reversible. Let me show you. Okay, so here's like the most famous quantum or reversible logic gate, where it's called the control-not gate. So remember I told you we tack on an extra bit of information that just goes along for the ride, it's untouched. So here, the C, initial, so we have A, B, and C, these are all initial. When C is set to 0, then we know that we're gonna, where are we? Oh, I think it's the other way. I have 2 flags. The control-not gate. Okay, so A and B are your control, and C is your target bit. So only when the 2 controls are both 1, then the target bit gets flipped. So here in this instance, only down here does something happen. So the initial bit went from 1 to 0. So if I give you the output without seeing this, you can always reconstruct the input based on what the 2 control bits were doing. Okay, so this is a reversible gate. Yeah. I'm sorry?
So
Yeah, and this one too. Yep, this one too.
does it matter if it's like how many of them do it, or is it always going to be this?
There are different versions of this. You can have one, like the first one I learned was just one control knot. This one has 2 control knots. And so you can put these together in clever ways to do what you want, to create whatever you want. And so we talked about this. We said, well, why do they have to be reversible? Like we said, that we only have reversible processes. And these logic gates can be represented by matrices. So for instance, the quantum not gate Here's the matrix, which represents it. So it transforms the 0. Remember, that just represents a column vector 0, 1. When you do matrix multiplication, you're multiplying that matrix with a column vector 0, 1, and then you get the result that's that column vector 1, which is 0, 1. So you can work it out. You can work out the details for yourself. And so now putting it together, just as you have circuit diagrams for classical computers, we can have circuit diagrams for quantum computers. So for this one, we have wires, which represents the time evolution of qubits. So say up here we have a qubit going along. Here we have a qubit going along. Here, this is our control. This is our target. Then we do it again. Now this becomes my control. Here's my target, and so on. So the effect of this actually just swaps the location. If this was A and this is B, after we do this 3 times, we have B up here and A up here. We can talk about details if you want to see. I just wanted you to see what a quantum circuit might look like. You may see these in papers. I think actually that Google paper, let me see if they have it. They do. So if you look at it, I know it's hard to see, but they have their wires, which are their qubits, and they have their quantum operators in there, just so you can see, like, what am I looking at? Well, it's just looking at time evolution of qubits going along a wire with gates along the way, and they pass through. Okay, I promised you, why do we care? Here's one of the 2 important algorithms. So this is just monumental. This was given in '94, but until now they weren't really able to realize Shor's algorithm, really effectively. So really RSA wasn't really vulnerable to attack until more recently. So in '94, Shor gave a polynomial time algorithm. So if we have an integer that has L digits, it takes L squared time to factor it. Why is this incredible? Well, for instance, I just looked this up. So there is a running list on Wikipedia of these long, hundreds of digits long numbers that they're trying to factor. So the most recent one happened, I think it was a month ago, in November. So it had 240 decimal digits, and it was 753 bits. And they were able to factor it using a classical algorithm. It took 900 core years of computing time on a 2.1 gigahertz Intel processor. So classical algorithms are just not practical. If you're trying to break a system, you're not going to use an Intel processor is what they're trying to show. It just takes a couple minutes on a quantum computer.
What's a core user? Is that like a regular person? What's a core user? Is that like a regular person here?
No, it's like in the cloud here. It's like many, many processors happening simultaneously, a core processor. Yeah. So look, this is old, what I wrote down here, but if we have 300 digits, it could possibly take 150,000 years. This happens in just a few minutes with a quantum computer. And so I have the example here. We don't have to go through the details, I'm sure.
How many?
Maybe 10 more minutes, and we'll wrap up.
You have 20 minutes more. I will go in this case to send this information.
Okay, thank you.
Thank you. I will be back, guys.
Okay. So Shor's algorithm, it's number theoretic. I'm not going to go through the details, but I set it up so that you can, if you want to experiment with it. So I taught that 2440 class I was telling you guys about, and we learned enough. This is based on what's called modular exponentiation. So you raise to a power, and then you see the result mod some number. It's awkward to do by hand, but you can write a little Python code, which I did, and it's here, it's shared with you, so that you can do this quickly. So if you want to get your hands dirty and go through the details of Shor, you have enough information here. So basically what it boils down to is that you've got to randomly, suppose you're trying to factor 30. You're randomly selecting a number between 1 and 30 so that the GCD of it and 30 is 1, meaning it's relatively prime to 30. could choose 11, 19, 29, so all of these are relatively prime to 30. Now that you have that in your hand, you compute this function, which is this exponentiation. So we take 11, we raise it to 0, we're working mod 30, working mod 30, we get 1. Their remainder is mod 30. 11 to the power 1 has a remainder of 11, mod 30. 11 squared, which is 121, has a remainder of 1, mod 30. So you work mod 30. What you're looking for is the period of this function. That period helps you unlock what the prime factors are. So the hard part about this was finding the period of the periodic function. So Shor showed this. He has a more sophisticated version of what's called Simon's period finding algorithm, which is another a more basic quantum algorithm. So Shor gave this. And so you're able to unlock the prime factors. Yes?
Does it start going backwards, or is that like the time? The 11
It just
or-
repeats itself. So the period is 2.
No, like F4.
So F5 would be 11, F6 would be 1, and so on and so
No,
on.
I'm talking about the powers.
Oh, the powers just keep going up. Yep. But you only do enough so that you see, all right, what's the period? When does it start repeating itself? I found the period. Obviously, we're doing it by hand. I gave you small values, super easy. We can do it by hand. But if n was not 30, but something gigantic, and you had to do this, good luck, right? It would take forever. How do I find the period of this horrible? First of all, it's hard to do this modular exponentiation. That's not so fast. So yes, what a headache. So here, I said your turn to try. You can mess around with this. Like I said, I'll share these slides with you, but I wrote a little Python code to do that modular exponentiation, so you can set up your own examples and then try to find the period of that function. You can just pop them in. Pop the 3 values in, and you can look for the period using the Python code to help you. And then also to compute the GCD, that's not easy either. If you have to do that by hand, it takes forever. Even just for small numbers, I do them in class, the whole board is filled, I gotta work back upwards, trying to find inverses of things. What a headache, right? So it's not so simple. If I have like a 300-digit number, you can see why a classical computer would struggle with trying to crack it. Okay, what's the other search procedure? What's the other procedure? It's a search procedure. So suppose I'm searching, suppose all of you have your name in a list. How many of you? 1, 2, 3, 4, 5, 6, 7, 10 of you. And I want to search for the person that has a certain birthday. I know one of you has a birthday, but I've got to search for the person that has a certain birthday. What if I want to find your birthday? But I start here. So I ask you, what's your birthday? No, what's your birthday? No, what's your birthday? No. Worst case scenario, how many times do I have to ask before I get to the right answer? 10, right? Worst case scenario, I'm searching an n element list. I don't hit the jackpot till the very end. Worst case, it takes me n computational steps.